Okay, so our speaker today is Norbert Bollendorfer, who's going to speak about black hole entropy from loop quantum gravity, generalized theories, and higher dimensions. Norbert?
Okay, thank you, Jorge, for the introduction, and hello, everyone. So, as already said, I'm going to be talking about some recent work on black hole entropy from loop quantum gravity, focusing on generalized theories and higher dimensions. And the work on which this talk is based on has been with three co-authors, Thomas Thiemann, Andreas Thorn, and Jascha Neiman. Okay, so let's go to slide number 2, so I can give you a brief outline of the talk. We're going to start in part 1 with recalling some basic ingredients of the usual entropy calculation in 3+1 dimensions. And based on those, we're going to formulate our expectations for the entropy calculation in higher dimensions in the second part. We will then go on in the third part to state the precise results which we obtained, first of all in the framework, the classical framework. In the fourth part, we will propose a quantization for those classical degrees of freedom and obtain an entropy. In part 5, we will look at generalized theories of gravity and what kind of an entropy we're getting there. And then I want to conclude with some discussion remarks, omitted points, and further research. So let's start with the first part. We're on slide number 4 now, entropy calculation basic ingredients. So the entropy calculation in loop quantum gravity has a rather long history, and many authors worked on it. Some of the most important works are cited up here. The basic idea is that if you have a black hole, you model its horizon as an isolated horizon. And then the non-trivial statement is if you use connection variables, then you automatically get a boundary degrees of freedom on the isolated horizon. And the idea is then that you count those degrees of freedom on the boundary, and you count them such that they are in agreement with the total area of the black hole. And if you do that properly, you find that the black hole entropy is proportional to the area of the horizon. However, you don't really get the prefactor completely correct, but you get a dependency of 1 over gamma, where gamma is the free Barbero immersive parameter of the theory. Now, there has been some recent work in obtaining the expected prefactor 1/4 in front of the area, and I will comment on this later on. So, in order to derive this result in the green box, several key ingredients are needed. And these ingredients are formulated on a spatial slice of this horizon, which we call H in this talk. So what you need is you need a boundary symplectic structure, which tells you which degrees of freedom you have. Here, it's written in terms of an SU2 Chern-Simons theory. So this A is a connection, or an SU2 connection. We have a boundary condition, which relates, in this case, the curvature of this connection to the bulk variables, in this case being the electric flux conjugate to the bulk connection. And you also have an area operator, which gives you a spectrum for the area, and that is important to know how much area you should associate to the quantum states you are counting. Okay, so let's go to the next slide, number 5, higher dimensions results in short. So when you think about higher dimensions and look into the literature, you see two things. First of all, it is known how to formulate isolated horizons in higher dimensions. This was done by several authors. And we also know that we can extend loop quantum gravity to higher dimensions. So the new things that we had to derive and that I'm going to present in this talk are the following. We need to generalize this boundary symplectic structure to higher dimensions. We need to generalize the boundary condition to higher dimensions. We need to formulate a quantum theory based on those variables. We need to do the state counting. In this case, we will show that we actually don't need to do the state counting because we can reduce the problem to the 3+1 dimensional one. Then you can, for example, look at log corrections, and you find that you get dimension-independent log corrections in accordance with results of Carlib. And in the end, you also want to look at generalized theories of gravity and see if you get the correct entropy there, and we will also comment on this later on. Okay, so let's go to the next slide, number 6. Expectations for higher dimensions, or slide number 7, going to higher dimensions, canonical variables. So we're going to start now recalling the formulation of loop quantum gravity in higher dimensions. On this slide, I just want to present the variables we're using and tell you how they are related to the ones we know from 3+1 dimensions. And in the following slides, I will give you more details on those variables. So in 3+1 dimensions, we're formulating loop quantum gravity using an SU2 connection A. So it's written in the first box there. So it has a tensor index small a. So it's a one form and has an SU2 index I. Which makes it essentially a connection. And then you can also, depending on your rotation, you can put a gamma in front to indicate that this connection has been modified with a Barbero music parameter. So it decomposes into the spin connection big gamma plus small gamma, the Barbero music parameter, times the extrinsic curvature, as written in the last line of the first box. Then conjugate to this connection, you have a densitized triad, which essentially is the square root of the spatial metric up to a rescaling with this free parameter. And then you find that A and E are canonically conjugate. And especially you also find that A comma A is 0, so the connection is self-commuting. Now, if you go to higher dimensions, these variables essentially generalize in a very direct way. So the variables we're going to use in higher dimensions, it will be an SO D+1 connection A. So D+1 space-time dimensions we're having, there we're using an SO D+1 connection. So for example, if we would be in 4 dimensions or in 3+1 dimensions, we would use an SO4 connection. Now that connection again has a tensor index A, so it's a connection. It has two Lie algebra indices ij running from 0 to d, which are antisymmetric, so it's in the adjoint representation of the gauge group. And again, you can show that this connection big A decomposes into a type of spin connection. The further details on this connection are not important for this talk, plus again a term which goes as the extrinsic curvature. Now also this term is rescaled by a free parameter, which we here call beta. I don't call it gamma because it's conceptually different from the Barbero music parameter, and for example, if you're in 3+1 dimensions, you can show that you could formulate this connection using two free parameters, so gamma and beta. Yes, and then it turns out again A and pi are canonically conjugate, the connection is self-commuting, and you essentially have the same structure as in 3+1 dimensions. Now, you can take this connection and you can construct a holonomy, you smear it along a curve, contract it with some generators of your gauge group. You can construct a flux from this conjugate variable pi by just taking pi, smear it over d-1 surface, contract it with some smearing functions, as you do in 3+1 dimensions, and then having those holonomies and fluxes, you can calculate the holonomy flux algebra, which will be essentially the same algebra as for the SU2 variables, just with SOD+1 structure in the proper places, for example, if you commute two fluxes. Okay, so let's go to the next slide, number 8, constraints. Now, I've told you the variables which parameterize our phase space. Now I have to tell you about the constraints which it is subject to. So since it is related to the ADM formulation, we have a Hamiltonian constraint and a spatial diffeomorphism constraint. We have a Gauss law, which is because of the internal SOD+1 invariance. But here we also have a simplicity constraint. Now this simplicity constraint is essentially you take two of these pi's, you antisymmetrize them over the internal indices and set this to 0, and this will tell you that the pi is actually a so-called simple bivector, so it's a product of some vector with index I and some densitized Vielbein E. We will talk about this in more detail later. Here you just need to know the phase space is subject to this constraint. Now there are no other constraints, so especially there is no torsion constraint as one usually gets in the canonical analysis of the Palatini action, and this constraint essentially has been removed by a process called gauge unfixing. I will comment on this more on the next slide. So all of these constraints are now first class, at least before you go to a singular smearing like holonomies and fluxes, where we of course know that the simplicity constraints become second class among themselves. Now, for this talk, what is going to be most interesting are actually the simplicity constraints. And for now, we just need to know how they act on an edge of a spin network. So this is known, and what they do is they select so-called simple representations of the group SOD+1. And these simple representations are labeled by a single non-negative integer, a big lambda. So it's essentially a label like the J in the usual SU2 theory. And if you want to compare this formulation to the SU2 theory in 3+1 dimensions, you find that the first non-trivial eigenvalue or the first non-trivial label lambda equals to 1 corresponds to taking a J plus equal to J minus equal to 1/2 if you decompose SO4 into two SU2s. Okay. So of course we also have to think about how the simplicity constraint acts on the vertex of a spin network. And we will do that later on, however, it will not be important for the first parts of the talk. So let's go on to the next slide, number 9, going to higher dimensions canonical analysis. So in order to get a bit more feeling for those variables, let me tell you how you can derive them using a canonical analysis. So you start with the Palatini action in d+1 dimensions. This is the action written at the left-hand part of the first box. So it's an action in terms of a connection A and its curvature F and the d+1 bind EI. So it's a space-time field bind. Now, so this connection is not exactly what we want in the end because it's transforming on a non-compact group. However, we will fix that in the end. But for now, we can just do the canonical analysis. So we do a d+1 split of this action when we find the symplectic potential written in the first box. So we have A dot times pi. Pi is exactly the thing we had on the last slides. And if you look at the last line of the first box, you see that pi actually decomposes into, again, a densitized field bind E. So we have EAJ times the square root of Q, Q being the spatial metric, times some normal Ni, which is a normal, which is essentially the normal on your spatial slice, and here in its internal version. So, and also it's written there that if the simplicity constraint is satisfied, written as pi times epsilon, epsilon making it antisymmetric, and this m bar just meaning all the remaining indices, then it follows that pi is given by this product there. Now there's, as is known, there's a topological sector in 3+1 dimensions, however we won't consider it here because we're interested in higher dimensions. Okay, and then you get your list of constraints and you're basically at the previous slide. Now, however, you want to apply this stability algorithm of Dirac to check if there are further constraints, and you find that there is a further constraint. If you take the Poisson bracket of the Hamiltonian with the simplicity constraint, you get a new constraint that we call D here. And you find that if you take the Poisson bracket again of S and D, then this is invertible on the constraint surface, so these constraints are a second-class pair. Now, however, what we do is we remove D by the process of gauge unfixing, and that is just, you think of D as being a gauge fixing for a gauge transformation generated by the simplicity constraint, then you drop D to be like independent of this gauge fixing, and then you just have to ensure that the rest of your theory is consistent, and this can be reached by modifying your Hamiltonian constraint. So this can be done, and then again, you have a theory just with first-class constraints. Now, as I told you, we still have this problem that the gauge group is non-compact with these variables. However, we can fix this problem by a canonical transformation to an SOD+1 connection. That can be done explicitly. If you want to know in short why it works, you can think about reducing this theory to the ADM phase space, so you would relate this connection to a spatial D metric. However, if you do that for Lorentzian and Euclidean theory, the ADM phase space is the same. So it's always in terms of a spatial D metric and its momentum, and there you can also guess that a canonical transformation to SOD+1 connection variables should exist. Okay, so that much for the canonical analysis. So let's go to the next slide, number 10, going to higher dimensions area operator. So the message here is rather short. So the construction of the area operator generalizes directly to higher dimensions. So you construct it in the usual way. You square the flux, or flux integrated over D-1 surface, take the square root, and this is your area operator. Now, the eigenvalues of this operator acting on an edge labeled with a simple representation with this label lambda look very similar to the SU2 case. So you just get 8 pi g times the free parameter beta times square root of lambda times lambda plus D-1. So there's an explicit dependence on the number of dimensions here. However, that is not really an issue at all. So you just have an area spectrum which looks very similar to the usual SU2 area spectrum. And with area here, I will always mean the area of a D-1 surface, so the volume of a D-1 surface. Big D again being the number of spatial dimensions. Okay, so based on this result, we can actually formulate a first expectation for the entropy calculation because we have this finite area gap. So we expect that the calculation goes through as in 3+1 dimensions. We would think of that we model the horizon as the boundary of the spatial slice, and we could then count the different possibilities of distributing the horizon area in terms of these area bits. And since the area operator is finite or has a gap, we should get a finite entropy, and the arguments for the statistics of the punctures should also be the same as in 3+1 dimensions. So we expect that the calculation should go through in some way. However, of course, the detailed calculations, of course, are more difficult, and we will fill in all those gaps later. Okay. So let's go to the next slide, number 11, dimensional analysis. Here I want to show that there's already some difference appearing when you think about how to construct the boundary condition. So recall that the boundary condition of the isolated horizon degrees of freedom in 3+1 dimensions reads that the curvature f of the Chern-Simons connection A is given by the flux, here written as sigma I. This sigma I is nothing else than taking the densitized triad, big E, and contracting it with a lower epsilon symbol. That gives you a 2 form, and now you have a 2 form which is Lie algebra valued. The curvature is also a 2 form which is Lie algebra valued. So the equations f equal to sigma makes sense. So they make mathematical sense because on both sides you have the same tensor and internal structure. However, if you go to higher dimensions, you already realize that this can't be that easy because the curvature of a connection that you want to use on the horizon is again a 2 form, which is Lie algebra valued. However, if you take the pi and construct a form from it, you get a d-1 form because you have to use this epsilon to construct the form. So there's a mismatch in tensor structure, so you can't just say f equals to pi in higher dimensions. Now there are basically two possibilities to fix this. So either you could say I want to keep using a connection on the boundary, then you would need to modify your boundary condition. So you could write something like epsilon pi is going as some wedge product of the curvatures with an appropriate contraction of the internal indices. This can be done. We will see later how it works. Or you could say, well, I abandon using a connection on the horizon and I will use some other variables which fit nicer in this boundary condition. And you could just say that, well, epsilon pi should be something like an Lij, so some function with which is Lie algebra valued, and then we just generate a form from it by using the epsilon symbol on the horizon slice h. So this double pullback here just indicates that this is a form which lives only on the horizon slice, which is codimension 2 in space-time. And this L later will turn out to be a so-called binormal of the horizon slice, so it's an antisymmetric product of two normals of the horizon slice. Okay, so that for the possibilities we have. So here I'm essentially done with formulating our expectations for higher dimensions, and we will go on now to the third part of the talk, which are the precise results in classical GR. Okay, so we are on slide 13 now, a geometry of the problem, 2 pictures. So here I've drawn 2 pictures which will be important in the calculations we're doing. The picture on the left-hand side is familiar from the earlier papers of the isolated horizon literature. So what we are seeing there is a part of a conformal diagram of the space-time we're discussing. So the 45-degree line is an isolated horizon, big delta. So it's a null surface because it's 45 degrees. And on this null surface, spatial slices can terminate, so we have drawn 2 spatial slices here, sigma 1 and sigma 2. And these spatial slices also terminate at spatial infinity, iota 0 here. However, spatial infinity will not be important in this talk. I mean, how to treat spatial infinity is written already in the first papers on isolated horizons, and we will not say any more about this in this talk. So, however, what will be important is that a spatial slice has a normal. A normal of the spatial slice will always be called a small n in this talk. Here it's written in its internal version with the index ni. And then also, since the spatial slices terminate on the isolated horizon delta, you can consider their intersection and call it h, big H, just being the horizon slices we talked about before. Now in this picture, which I would call the covariant picture, several important calculations have to be performed. So first of all, we have to show that the Palatini action gives us a well-defined variational principle if we use the isolated horizon boundary conditions on delta. And we also want to show that we get a boundary symplectic structure so that we have boundary degrees of freedom. However, since this is a covariant picture, in this picture we are always working with a non-compact internal gauge group. However, we wanted to change that to an internal compact gauge group for quantization purposes, and that we can do in the canonical picture on the right-hand side. So the canonical picture just focuses on a single spatial slice, which could be anywhere in space-time. And the spatial slice is again denoted by sigma. it has again a normal Ni. Now this normal has to be internal here because in the Hamiltonian formalism there is no good way of saying that you have some time-like vector or so. So we have this internal normal. Now also, as said, the spatial slice terminates on the isolated horizon, so it has a boundary which is this horizon slice, big H. This boundary is now codimension 2 in space-time. And again, the right boundary of the right-hand side boundary of sigma, this spatial infinity, we will just neglect. Now, since big H is codimension 2, it has a second normal, and this normal we will always denote by small s in this talk. So this normal small s, it will lie within the spatial slice sigma, and here we have written it again in an internal version. So since it's inside sigma, we have n times s equal to 0, so they are orthogonal. Now on later slides, I will use several versions of this s being denoted with some twiddles or hats or so, and they are basically the appropriate objects to use in certain situations. However, you should always imagine these s's as just being a normal on this horizon slice. Now, as said, in this canonical picture, some other important calculations have to be done. For example, we want to switch to the compact gauge group SOD+1, and the canonical picture is also important for doing the computation that we want to use a Chern-Simons type variables later on. So later on, we're going to show that we're going to use essentially higher dimensional Chern-Simons theory on the horizon. Okay. So let's go to the next slide now, slide number 14, action principle and covariant canonical framework. So on this slide, we're essentially doing the calculations of the left-hand side of the two pictures. In the covariant framework. So here we start with the Palatini action that we already saw before. So it's just this curvature wedge, this big sigma, which big sigma here usually is denoted by this E wedge E and then the Hodge star. And we're going to introduce no additional boundary contribution on the isolated horizon. So if you recall that if you're using an action for gravity, you have to put some, or you might have to put some boundary contribution on the boundary of your space-time in order to get a well-defined variation principle. But here on this isolated horizon boundary, we're putting no boundary contribution. So since we didn't put any boundary contribution, when calculating the first variation of this action, we pick up a boundary term, which is written down in the second box. This boundary term being an integral over the isolated horizon of sigma wedge the variation of A. And what we have to show in order to get the usual equations of motion, we have to show that this term actually vanishes if we impose that delta as a non-rotating isolated horizon. And this can be done, well, you get a 0 from the calculation. So in this talk, I actually want to spare you the details of what is the exact definition of a non-rotating isolated horizon, because it doesn't help at any point in this talk to know what is the precise definition. If you're interested, you can look at the very last slide of this talk for a definition, or you should look in the papers for more details. But again, for this talk, the definition is not really important. So then, having shown that the first variation vanishes, you're next interested in the symplectic structure. So what you want to calculate is the second variation of your action. So you take another variation of the formula in the second box, and then you get the third box. So it's an integral over delta of delta 1 sigma wedge delta 2a. The delta is anti-symmetrized. And what you want to show now is that this reduces to a boundary contribution. So this integral should reduce to an integral over h2 minus an integral over h1 of the boundary symplectic structure. And that, again, can be done if you're using that it's a non-rotating isolated horizon, and this then gives you the boundary symplectic structure. Now, how this boundary symplectic structure looks like, I will tell you on the next slide. Okay. So let's go to the next slide, number 15. Boundary symplectic structure and boundary condition. So let me remind you again of the variables we are using. So we are using an SOD+1 connection, big A. Conjugate to that, we have a densitized hybrid vielbein pi, meaning essentially that it's again a square root of the spatial metric, and these two are conjugate to each other. Also recall that in the canonical picture, we had this internal normal small ni being the normal on our spatial slice. I also told you before that this pi on the constraint surface of the simplicity constraint, it decomposes into the product of two vectors, so that is also in the second line of the first box. So pi on the constraint surface is given by this ni times the densitized vielbein, and then you also have this free parameter there, this free parameter beta. Now also recall we had this normal Si being the normal on the horizon slice. Again, we can write it in several different versions. We can write it as Si, we can write it as Sa as a vector, we can write it as twiddle I being a densitized normal, so we densitize it with the square root of h being the metric or the determinant of the metric on the horizon slice. So this we call an area density because it's a codimension 2 density. And then if you recall all those definitions, you can go to the second box and look at the symplectic structure. So let me remind you again what's happening in 3+1 dimensions. So there, when you do the calculation, you find that the symplectic structure is actually written as an integral over h of delta 1 e wedge delta 2 e. So it's written in terms of the triad. However, then in the second step, you can show that this actually can be rewritten as delta 1a wedge delta 2a. So you can rewrite this as the symplectic structure in terms of a connection. Now, something very similar is happening also in higher dimensions. So in the first step of the calculation, you get that the symplectic structure is an integral over h of delta 1 s twiddle times delta 2n. So the conjugate variables are the normal n and the densitized normal s twiddle. And then you're essentially in this first situation that you have the triad as a horizon variable. However, you might want to use a connection on the horizon, and you try to rewrite this symplectic structure in terms of connection. And this can also be done, and the formula is written on the right-hand side of the second box. So let me tell you what symbols are there. So first of all, this is the symplectic structure of a higher dimensional Chern-Simons theory. So this Chern-Simons theory is written in terms of a connection which is called gamma 0 here. So the form index is suppressed. So this gamma 0 ij, it has the same internal structure as our SOD+1 connection A. However, it's a connection living just on the horizon slice. So how is this connection defined? It's defined in the second line of the second box. So it's defined as taking the covariant derivative of this connection, and this covariant derivative should annihilate n, s, and the double pullback of the space-time vielbein to the horizon slice. So given these three requirements, gamma 0 is determined uniquely, and you can then use it. And then you can also construct its curvature, which we call R0 here. And then if you do all the detailed calculation, you find that the left-hand side of the second box is proportional to the right-hand side of the second box, and the factors I have suppressed here, they're just trivial numerical factors. So the non-trivial factors appearing in this proportionality are written there as the area of the horizon slice, AH, the Euler characteristic of the horizon slice, chi, and the free parameter beta. Okay. So that is the...
Technical question.
Yes?
Yes, this is very impressive to be able to get to the higher dimensional Chern-Simons theory. Is there also a route to it through adding a boundary term to the action, which is the higher dimensional Chern-Simons form? I guess it would be gamma 0, wedge R, wedge R, wedge R.
Yes, so we haven't done that explicitly. I know this has been done, I think, in the first paper of Abai and collaborators in the U1 framework, but this would be something one could try, yes.
Yeah, if you started through the Plebanski rather than the Palatini formulation in 3+1, then I think you do need to add a boundary term, which is the Chern-Simons action. But if you go through the Palatini form, I think you're right that you don't.
Okay.
Is that true also in higher dimensions?
Well, yes. So you don't need to add a boundary term if you use these non-rotating isolated horizon conditions I've told you on the previous slide. Yes.
Right. And is there an analog of the Plebanski action for these higher dimensional theories? Rather than the Palatini?
Yes, there should be. Yes.
Okay. Anyway, it's a technical discussion, but it's very beautiful that this all works out in higher dimension.
Okay.
Thanks.
Thank you. So let's go to the third box now. So we also need a boundary condition. So recall from 3+1 dimensions again, the boundary condition is the curvature of the connection A is this sigma of the flux E. And we want to generalize that now to higher dimensions. So we just take our this pi, contract it with the normal on the horizon slice, and put such a double pullback epsilon there to make it into a d-1 form. And then this basically trivially is proportional or is the same as 2 over beta times n times s twiddle times this epsilon. This we just get from the solution of the simplicity constraint. So this already gives us a good boundary condition if we use n and s as horizon variables. But then in a second step you can again show that this is proportional to the expression on the right hand side. So there we have a wedge product of these curvatures R0. We contract them with an internal epsilon symbol. Then we have two free indices ij, and we find that we get n times s. Again, there is some trivial prefactor which I suppressed here, and the non-trivial prefactors are again the area of the horizon slice, Euler characteristic, and the free parameter. It's actually very, very simple to derive this boundary condition and that is essentially how we did it in the first place. So basically from the construction of this gamma 0, you can conclude that the curvature R0 should be orthogonal on both n and s. So if you contract R0 with the internal vectors n and s, then you get 0. And then you find that this ij indices on the epsilon symbol, they can only be proportional to n and s because the r's are orthogonal to n and s. And then you just have to figure out the prefactor. Okay, so these are the boundary variables we can use. So the situation we are seeing here that we have actually two choices of boundary variables. So we can write it in terms of a connection, then we have a higher dimensional Chern-Simons theory. However, when we want to quantize that, we found it's a lot harder than in 3+1 dimensions, because higher dimensional non-abelian Chern-Simons theory has local degrees of freedom. And quantization is essentially not known, so I'm not aware of any paper where this theory is quantized. And also we are restricted to d+1 even space-time dimensions, because essentially for all those wedge products you always get 2 more dimensions, so you can, for example, go into 5 dimensions. However, the metric variables n and s twiddle, they are easier to handle, especially their symplectic structure is more easy, and they allow for dimension-independent treatment, as I want to show you in the next part of the talk.
Okay. Can I ask you a question at this stage?
Sure.
Norbert, so in your second box, you got this gamma naught, and you said something about uniqueness.
Yes.
As I understand it, physically, you only have this derivative operator d, the physical metric, the
Yes.
physical configuration that you have, gives you this derivative operator capital D on the boundary.
Yes.
So how is gamma naught unique? I mean, is there no gauge freedom in it? I mean, what is the claim here?
There is a lot of freedom in defining this gamma naught, and I actually won't tell you, or didn't plan on telling you the details in this talk. So the statement I made, giving the conditions dn is 0, ds is 0, and de is 0, gamma naught is uniquely defined. But the other question is, can I define some other gamma naught such that the boundary condition and the boundary symplectic structure still look the same? And the answer to this question is yes. And there is freedom in defining this gamma naught. Here I've just given you a specific choice of gamma naught.
I'm still confused. Okay. So you're saying that there is a, yeah, I see. Okay. So
Okay.
why can't I make a gauge transformation? Is what I cannot make a gauge transformation. You're saying on gamma naught.
You could make gauge transformations on gamma naught, but there are more non-trivial things you can do. You can really change the connection to a different connection.
No, but I'm just looking at the trivial part. I mean, I think somehow you are saying that you know what little d is, and then those conditions on capital D determines gamma naught. But you don't know what little d is.
No, I
And the whole point about gauge transformation is I can change little d and make a gauge transformation on gamma naught at the same time.
With little d, I mean the partial derivative without any
Yes,
connection.
partial derivative. Right, but that is just coordinate derivative, so I could just change those coordinates.
Yes.
So capital D I cannot understand how capital D would determine a unique gamma naught. You're putting conditions on capital D. Okay, I'm just confused about what is being said here. I mean, if I'm just given a manifold, you're saying that there's a unique gamma naught, such that something is true.
No, what I'm saying, if you take n, if you take the small d being a partial derivative, and you impose those
coordinates.
Excuse me?
With respect to what coordinates? You can choose a set of coordinates, and I can change the set of coordinates, right?
Okay.
So for each choice of set of coordinates, gamma naught is unique. But then I can change coordinates, and then gamma naught will be different. It will be gauge transformed.
Okay.
So therefore, gamma naught is not unique. It would seem to me.
Okay.
So I'm confused about your claim.
Okay, but even if gamma naught is not unique, it doesn't change the fact that you get this symplectic structure and the boundary condition.
Okay, but then why is the boundary term gauge invariant? Because if I did what I did just now, which is to change the coordinates and therefore make a gauge transformation on gamma naught,
yes,
then it would seem to me, just by inspection there, that it is not obvious at all that the boundary term you have written down is gauge invariant.
Variation of a connection always transforms at the vector.
Okay, let's keep going, please. Thank you.
Okay. So
another question.
Yes.
For the distinction, I'm confused about the distinction between saying that the isolated horizon has local degrees of freedom when described in terms of the higher dimensional Chern-Simons connection. They are not there described in terms of metric variables. Is the physics of the isolated horizon different in the two descriptions? Or does it also have local degrees of freedom in the metric variables that are easier to control?
Well, of course you can't. Of course, classically the descriptions are the same because it's just a canonical transformation. I mean, the question is, what happens if you quantize one set of variables, and what happens if you quantize the other set, given this boundary condition? So what do you get in the end? And then there's also the question, which boundary condition should you actually use? I will make a comment on that later.
But just for a point of information, does the fact that Chern-Simons theory has local degrees of freedom in 5 or more dimensions but doesn't have them in 3 dimensions imply anything about the physics of isolated horizons in higher dimensions as compared to 3 dimensions?
No, not that I know of, because again, it's a canonical transformation. So all the degrees of freedom at the classical level are already captured in N and S. So at the classical level,
so it's not that there are additional degrees of freedom which are somehow appear for isolated horizons.
No, it's more. My understanding right now is more that it's a bug in the quantization actually, if you use the Chern-Simons.
Okay, but there have to be classical implications of this. Anyway, let's go on. It's a very interesting question.
Okay. So let's go on to the first part of the talk now, quantization. So we are now on slide number 17, problems with Chern-Simons theory. So as just discussed, Chern-Simons theory, or higher dimensional Chern-Simons theory, is rather complicated, and it has this complicated symplectic structure written in the first box. And if you, for example, try to calculate the Poisson bracket between two connections, this is a very complicated thing because you would have to invert for that this wedge product of the R zeros there. So, however, if you fiddle around a bit, you find that there's actually an easy subset of phase-space functions in the higher dimensional Chern-Simons theory which have an easy algebra. So, in order to find out what they are, recall the boundary condition. Pi, by the boundary condition, this is this n times s twiddle. This we will call Lij in the following. This was the Lij from one of the previous slides. And this, again, by the boundary condition, was proportional to this wedge product of the R's. Now, if you compute the algebra between those functions, for example, of the n times s with the symplectic structure of the n and s, you find that L, L is again given by L times some structure constants. And you can repeat the same thing using the Chern-Simons symplectic structure, using this wedge product of R's. You get the same algebra, but this is obvious because they are the same thing and the Poisson brackets are related by canonical transformations. So we have these degrees of freedom there, which have an easy algebra, and furthermore, they are very accessible to our boundary condition because they enter the boundary condition explicitly. So in some sense, you would want to use those variables now. However, of course, if you use the Chern-Simons theory, there are different phase-space functions in the Chern-Simons theory which you would want to quantize. However, it seems at the moment that or to me, that they're physically kind of irrelevant for the entropy calculation. You might even try to remove them by some stronger boundary condition. So we commented in our paper with Andreas and Thomas on that by imposing a boundary condition which is actually stronger than the boundary condition written up here, which would be something like the curvature R0 is some function of the triad, and then to regularize that, and that would maybe project you to no local degrees of freedom. But it's not really clear if that works, and I want to leave it open for now. But the statement here I want to make is that this problem is completely avoided if you just stick to binormals as horizon variables. So you just use n and s as variables on the horizon, and you want to try to quantize them. And that is what we're doing on the next slide, slide number 18. So there we again consider these L's, which are just n times s. We can smear them over some surface S to make them more regular, and then if you calculate their Poisson bracket, we have L, comma L is again L with some structure constants, and these structure constants are just the structure constants of the Lie algebra SOD+1. So this is actually similar to something which was already observed in the SU2 case by Engel, Nui, Perez, and Francetti, who said that you could also use the triad or a flux as a variable on the boundary, and they have also this SU2 algebra. So now, having those boundary variables, how would our Hilbert space look like of the boundary? Well, it's just a product of representation spaces of SOD+1, because the algebra is just the SOD+1 algebra. And now, having this big product of representation spaces, we implement the boundary condition pi equals to L, so flux equals to these L's. And this just tells us that these representations are non-trivial only at points where the spin network punctures the horizon, or where a spin network punctures the horizon. And by this boundary condition, we also get that the representation on the horizon is the same representation as of the incoming spin network edge. Okay. Then there's also another constraint you want to impose, which is kind of off-diagonal horizon simplicity constraint. And this constraint, you can derive it from looking more closely at the properties of a non-rotating isolated horizon. So for those of you who have looked at those calculations, you might recall that an isolated horizon is defined in part by a null normal, small l. And this null normal has a property that if you take the covariant derivative of this null normal, this reduces to some one form omega times this null normal. And this one form omega vanishes if you pull it back to the horizon slice. So this equation would basically read covariant derivative of L double pullback is 0. Here something similar happens. So here we have double pullback of K equal to 0. This Ki just being the sum of N and S. So for those familiar with the isolated horizons, this K is just the second null co-normal. So if you have an isolated horizon, you have a null normal L, you have a co-normal K, and then you also have the directions orthogonal to that, which are the directions of the horizon slice. Now the fact that here the derivative of K is 0 just comes from the fact that we're using a compact internal gauge group. If we would use a non-compact internal gauge group, this equation would read derivative of L is 0, or derivative of small l is 0, L being the null norm. However, the argument we're making is invariant of this choice of compact or non-compact group, because if you consider this big L, ij, you can show that it's a product of small l and small k. And since basically k is constant, what you want to impose is that L at one point and L at a different point, they should share a common vector. And this is imposed by an off-diagonal simplicity constraint. So you just take L smeared over some surface S1 times L smeared over some surface S2, approximately, or 0 on the constraint surface. Now there is some slight hand-waving in this argument, because essentially the condition covariant derivative k equal to 0, of course, does not impose a partial derivative of k equal to 0. However, imposing this condition is essentially the best you can do when using these L's as horizon degrees of freedom. And on with another argument, you might say that, well, in the end, what we want to do is we want to count degrees of freedom on the isolated horizon. So it's only important that we get the degrees of freedom right. So if you impose a condition which should restrict the same degrees of freedom, then we're fine. And this is exactly what this off-diagonal horizon simplicity constraint does. And then there's also some issue with imposing it on just contractible charts of the horizon slice that essentially should give you topology corrections if you go to higher genus surfaces, for example. Okay.
I'm confused about the notation here.
Yes.
What is S is to surface, right? S is the cross section of the horizon.
Yes, D-1 surface, yes.
At D-1. And so we're, sorry, D-1 surface. And now we are in the canonical picture, right?
Yes.
So what does, I mean, in the last box, you have, in the last box, you have got this big Lij subscript S1 and S2. So what is S1 and S2 there?
These are just different surfaces over which these L's are smeared. So you could think of the S1 being a surface, an infinitesimal surface around a point x1, and S2 an infinitesimal surface around another point x2.
So this is now in the bulk. Is that what you're saying?
No, they are smeared as on D-1 surfaces which are living on the horizon slice H.
So S1 and S2 are not D-2 dimensional surfaces?
No,
the horizon is just a D-2 surface, right?
S1 and S2 are D-1 dimensional surfaces, D being the number of spatial dimensions. So the horizon slice H is also D-1 dimensions.
All right. Okay, so, sorry, D is okay, so S1 and S2 are D-1. So S1 and S2 don't coincide with the horizon? I mean, can they be?
No, they have to be on the horizon. They are on the horizon. Okay.
But horizon is also D-1 surface, right?
Yes.
So they're just small patches of the horizon.
Yes.
But how do you compare? I mean, I got L at one point and L at another point.
Yes.
And so what does that skew symmetrization mean? I mean, these internal indexes, I mean, you're not transporting anything from one point to another point.
Exactly. That is what I said. So essentially, if you want to impose such a constraint exactly, there would be some parallel transport involved, which also then would tell you that the covariant derivative of K is zero, not its partial derivative. However, you can't really you can't impose that there because you don't have a connection on your isolated horizon. If you're just using this binomial.
Right. Yeah, exactly. So what does that condition mean?
Yes. So you can write that condition down. Well, what it does, it breaks local gauge invariance on the horizon slice. So you restrict yourself to global gauge invariance on the horizon slice. That is the sentence written in the next line. So this is an explicit breaking of the gauge invariance. However, this is not a. Yes.
Let me go back to the middle box, boundary Hilbert space. I can understand several statements here. Why is the boundary Hilbert space product of SOD1 representation space? What kind of quantization are we talking about? What is the configuration space, or the phase space? And then, I mean, how is it achieved? How do we know? Why do we say this?
Yes. So essentially, if you look at those L's, these L's have the algebra of SOD plus 1. So essentially, what you expect is you get SOD plus 1 representation spaces because that's just the representation of the algebra written up there. Now, you would want to regularize that in some precise way. So what you would do is, given some point on your horizon slice, you would take some surface, which is basically a smearing around this point, integrate the L over it so the L is more regular, and then you would shrink that surface to a point, and then define with this regularization, you would define the Hilbert space at this point. And then the total Hilbert space would just be a product over all those Hilbert spaces, and well, that would be your horizon Hilbert space. On that space, you would impose the boundary condition, which tells you that most of those Hilbert spaces have trivial representation, and the non-trivial ones are just where the spin network punctures.
Thank you.
Yep. Okay. So this breaking of local gauge invariance is actually not a problem at all for the calculation, and something similar already happens in the U1 case, however, for different technical reasons. You can, for example, read on that in Thomas' book. Okay. And then more locally covariant quantization of this off-diagonal simplicity constraint might be achieved if you could handle the higher dimensional Chern-Simons theory, because there then you have a connection. However, again, we can't do that at this moment. Okay. So let's go to the next slide, number 19. Here in the first box, we just collect what we've said before. So our horizon Hilbert space was this product of the SOD plus 1 representation spaces. So then comparing with the treatment of U1 and SU2 in 3 plus 1 dimensions, you would expect some kind of global gauge invariance condition. So you would expect that your horizon is actually an intertwiner, an SOD+1 intertwiner. This can be derived explicitly in the U1 case by taking a loop around all the punctures and contracting it around the back of the sphere. And with the SU2 case, it's already more difficult, and you have to appeal to the quantization of the Chern-Simons theory. In higher dimensions, we don't have some clear-cut argument to derive this, so essentially you have to argue that this is true. You could, for example, follow arguments of Rowley and Krasnov, or you could compare how you would solve certain constraints at the classical level and the quantum level and see what is physically more suitable. And more details on that are given in the third paper cited at the beginning. So, however, when you accept that there should be an intertwiner, you can say, okay, what's the next thing? So we have the simplicity constraints of the bulk, which tell us that we have simple representations in the bulk. Now, by the boundary conditions, we also have the simple representations on the horizon now. And we had this off-diagonal simplicity constraints from the previous slide. Now they become, or they are second-class constraints using the symplectic structure we're having, and we are in the same situation as one is usually faced with the simplicity constraints. So we have to use a strategy to quantize them. And what we use here is we use the strategy which was proposed in a paper with Thomas and Andreas. That is, we're selecting a maximally commuting subset of these simplicity constraints, and this results in the concept of a simple intertwiner, which is an intertwiner which is simple in a given recoupling scheme. So when you have that solution, you recall that there is actually a one-to-one mapping from these simple SOD+1 intertwiners to SU2 intertwiners. And then when you have established that, you have essentially reduced the counting problem to the 3+1 dimensional one, because you have shown that the Hilbert space has the same size as the Hilbert space of an SU2 intertwiner. And then you just look at the counting, how it's done, and you find that, well, if you would count the entropy, you would get, again, something proportional to the area over the free parameter. You would get some constant, which now depends slightly on the number of dimensions you're in, and you get a universal logarithmic corrections of -3/2 log A. And that is nice because it's in agreement with results of Karlip and Solodukin, which were obtained using conformal field theory methods. Now, when you look at this simple intertwiner, when we proposed that, there were essentially two issues which were open with this proposal for solving the simplicity constraint. The first one was it actually depends on the choice of recoupling scheme, and the second one was it's probably not going to be anomaly free with the Hamiltonian constraint. However, both of these critiques don't apply in this case because the choice of recoupling scheme does not change the number of degrees of freedom such an intertwiner has, and also the Hamiltonian constraint doesn't enter this calculation because it vanishes when you go on the isolated horizon, as one knows from the other isolated horizon entropy calculations. So what I've told you on this slide is going to be compatible with what I'm going to tell you in the next chapter, where we are going to talk about generalized theories and the wall entropy. And it's also compatible with an analytic continuation in the free parameter, as was proposed recently by Freudengeiller, Nui, and Perez. Okay, but I'm not going to say more about this last part in this talk. Okay, so let's go on then to the next part, number 5, generalized theories. So we are on slide number 21 now. So here, let me first tell you what I mean by a generalized theory. So by a generalized theory, I mean a theory which we define by an action as an integral over the metric density times some Lagrangian. And this Lagrangian is just a function of the metric, the curvature, some derivatives of the curvature, matter fields, and also derivatives of the matter fields. And then if you have such a generalized theory of gravity, it was Wald who proposed that there is a sensible notion of entropy, which you can derive from the first law. And this entropy is today called the Wald entropy, and it's written in this red box. So it's 1/4g, an integral over the horizon slice of the area density. But then it's modified by a variational derivative of the Lagrangian with respect to the Riemann curvature and contracted with two binormals epsilon. These epsilons here, they're just essentially the L's, so they're a product of n and s, anti-symmetrized, and with them you contract this field strength tensor. Now this is in general different than area over 4g for generalized theories, and we have to think about what's happening in ILQG. So if we consider such a generalized theory, would we still get area or would we get something else? Hopefully we would get the Wald entropy. Okay, So just for those who don't know much about the wall entropy, so the wall entropy is essentially the agreed upon formula of how an entropy should look like for a generalized theory, and there's remarkable there's remarkable evidence that it is good, for example, from calculations coming from string theory, where you compare computations done on microscopic degrees of freedom with an effective action derived from these degrees of freedom, and they match incredibly well. So here in this talk, I can't consider all generalized theories of gravity for technical reasons. So what we are considering here is we consider theories which can be written on the phase space of GR plus standard matter. And this essentially tells us we don't have higher time derivatives which would enlarge our phase space. And the class of such theories is given, for example, by Lansell's Lovelock gravity, plus, for example, non-minimally coupled scalar fields. And the presentation I'm going to make here, it will be in the context of 3+1 dimensions for easier recognizability. However, it also works in higher dimensions. Okay, so let's go to the next slide, number 22. Generalized gravity theories. So let me remind you what's happening in pure GR. In pure GR, the connection and the momentum both have a standard geometric interpretation, meaning that the connection A is given by the spin connection gamma plus the extrinsic curvature, and the densitized triad is just the square root of the spatial metric. However, in a generalized theory, those statements are not true anymore, because consider, for example, the connection A equals gamma plus the extrinsic curvature, and think about what its conjugate momentum is. In order to derive that, you just take the Lagrangian, you take the partial derivative with respect to the time derivative of the connection, and you get the conjugate momentum big P here. Then A and P are conjugate in the Poisson bracket. However, if you now look at P, then you find that in general it's not just the densitized triad. And the first example I want to give you here is take as your Lagrangian just a non-minimally coupled scalar field. That is, it's the Ricci scalar times some function A of the scalar field phi. Then you find that this P is given by A of phi times E. So A of phi is not the densitized triad, but something more general. And more discussion on this point is in my ILQGS 13 talk, which is available online. And there I also discussed that there's actually a choice or there's some ambiguity in this choice of connection when you have scalar fields. But I won't say anything about that here due to time reasons. Okay, so let's go to the next slide, number 23. Here we basically investigate what's happening to this big P. So we're interested what's happening to this big P on the horizon slice, because there it enters the entropy calculation. So if we look at this big P there, we find that the relevant component of the big P, which is the P contracted with the horizon normal S, is given by, again, the densitized triad big E. However, it's modified by a derivative of the Lagrangian with respect to the Riemann curvature contracted by our two binormals epsilon. And this is very nice because this is just the wall entropy density divided by the area density times the densitized triad, which essentially provides us with a vector value area density. So this expression is nothing else than a vector valued wall entropy density. So if you now construct the generalized area operator in this theory, here we call it area twiddle, you construct it as an integral over the square root of p squared as the usual area operator. This operator has the same spectrum as the area operator because the p has the same algebraic properties as the flux has in loop quantum gravity. However, this operator, it does not measure the area, but it measures something more general, and in the first box we see that what it actually measures is the wall entropy. So in a generalized theory of gravity, the area operator is substituted by a wall entropy operator, at least when you evaluate it on a horizon slice H. Now, I have to tell you what's happening now with the isolated horizon calculations given this substitution, and the answer is very simple. So everything goes through as before, just at the end you have to substitute the area by the wall entropy. And here there's also a comment on the connection, for example, that you would use on the horizon there. So in this case of this generalized theory, you could use such a gamma zero built from any vielbein as such that the area density you derive from this vielbein is given by the wall entropy density. So here we see already that there's lots of freedom in choosing this horizon connection gamma. Okay. So I will comment on this wall entropy thing a bit more later on. Okay. So yeah, so let's go to the next part then, discussion and remarks. So we are on slide number 25 now. So the first remark I want to make is that it was rather striking to me that the area operator is substituted by a Wald entropy operator, at least when you evaluate it on an isolated horizon. And that is interesting for several reasons. First of all, the area operator is essentially the only operator which has an easy spectrum in loop quantum gravity. So it's basically, it measures what the labels of our spin network are. So, so this now raises issues for the interpretation of spin networks, because, for example, one of the favorite interpretations is that of a twisted geometry. However, now the last slide, it essentially told us that we should think of this recoupling labels, or of these labels of the spin network, really as describing entropy and not as describing area. And this is for the very fact how the area operator is actually constructed from the beginning. So the area operator is constructed as the magnitude of a flux, but the flux is just a derivative of the Lagrangian with respect to the time derivative of the connection, which again is just a derivative of the Lagrangian with respect to the curvature. So classically, this really corresponds to a Wald entropy instead of an area. An area is just a very peculiar thing for using standard GR. Okay. And this also then raises issues if you want to go to other geometric operators like the volume operator or the length operator, because they don't seem to have any good interpretation if the flux is actually not measuring the area, but it's measuring the Wald entropy. Then if you take the flux to the 3/2, for example, for the volume operator, it's not really clear what it should mean geometrically. Okay. Another thing, the quantization of Wald entropy is expected from general arguments, starting with Bekenstein. Here's a review paper of him. He did it for pure GR, but this was also generalized to Lance's Lovelock gravity by the people with a second citation there. And then also again, the most important ingredient of the theory we have on our horizon is the area density in the end, or in more general situations, the Wald entropy density. So again, I didn't say much about this freedom in choosing the connection, but there's essentially lots of freedom for doing canonical transformation using different connections on the horizon. You could even introduce a different free parameter on the horizon, which is something which was already noticed by Engel, Perez, Nui, and Pranzetti in 2010 in the SU2 case, where they say also there you can use a different free parameter on the horizon. Okay. So let's go on to the next point then, omitted points and further research. So we are on slide number 27 now. So what I didn't tell you about today is that there's an ambiguity in the choice of connection on the horizon, especially when you have scalar fields. This more discussion on that is in the Loops 13 talk and also in the paper cited there. And also there's a polyhedral interpretation of these results. So essentially this interpretation of an SU2 intertwiner as the polyhedron, you can generalize that to higher dimensions and interpret a simple SOD plus 1 intertwiner as a higher dimensional polytope. And this is also in the third paper cited at the beginning of the talk. Now, further research which might be interesting is obtaining the prefactor 1/4 in the beginning of the action. So there are several new developments in this line of research. What I didn't mention yet is the papers by Gosch, Frodden, and Perez. And it would be interesting to see if this generalizes to higher dimensions. It probably does directly. But then you are also interested in what's happening for generalized theories. So do you get the correct Wald entropy? And even, for example, if you use some different connection which does not give you even the correct dependence on the Wald entropy in the entropy formula, would the ideas of Gosch, Frodden, and Perez even repair such a transformation? Okay. So then, of course, we would like to quantize the higher dimensional Chern-Simons theory on the boundary. That is probably more rigorous than what we did here, but it's again very hard because of these local degrees of freedom. It would be interesting to extend everything to generic isolated horizons. So here we use the non-rotation condition in several calculations. One might be interested in computing topology corrections. So already in 3+1 dimensions, where you can show that in the context of an ADS or locally asymptotic ADS space, you can have non-trivial horizon topologies. There you can compute topology corrections to the entropy, and it would be interesting to do that also in higher dimensions. And in the end, of course, one might also be interested in supergravity and there an isolated horizon framework exists, but we haven't done any calculations there yet. Okay, so let's go to the last slide, number 29. Let me just briefly summarize. I've stated several classical results, starting with a non-rotating isolated horizon. You can show that the action principle is well defined. A boundary symplectic structure can be derived and a boundary condition. If you do that for a generalized theory of gravity, everything works as before, but essentially the area operator becomes a walled entropy operator. The entropy goes then as walled entropy. And if you quantize the system, you are in trouble when you're trying to quantize the higher dimensional Chern-Simons theory. We don't know how to do that yet. However, a largely dimension-independent treatment is possible using these densitized binormals. And this quantization is actually very useful for studying of how to impose the simplicity constraint, because this simplicity constraint would then enter the logarithmic corrections of your entropy. So thank you very much for your attention.
Questions?
No, but I realize that most of my questions are really confusions about what you're fixing in your boundary condition of the horizon and what you're not.
Mm-hmm.
So if I go back to your slide 18,
Yes.
Okay, on the top line, the top box up here, you have defined Lij as S. And S there is just a local patch of the horizon. Is that correct?
Yes.
Okay. But that, I mean, when integrals of that kind you are written down, they are not gauge invariant, right?
Yes.
Because if I apply local gauge transformation, then I will they will be rotated by an arbitrary group element, and when I integrate, I get.
So
This is at each point.
Yes. So essentially,
when I get what I get on the right, left hand side is just complete.
Yes. Yes. So the idea, what you want to do there is, you want to get rid of this delta distribution, which you get when you have L at a point and the L at some other point. So in order to do that, you would smear it over a surface like a flux operator in loop quantum gravity, and then here these S's, you would actually shrink them to a point. So and then compute the algebra of the L's in this limit where you shrink that to a point, and in this limit where you shrink it to a point, they become a gauge invariant again. So it's actually very similar on I mean, if you calculate a flux in loop quantum gravity, it's also not really gauge invariant in exactly this sense.
Right. So there we sort of explicitly say that it is in a certain gauge, right? You fix a gauge and then you get this object. We don't try to attribute to it too much of a gauge invariant significance by itself.
Mm-hmm.
But here your basic algebra, which you wrote down on the next line, the points of bracket thing. So those LSs are not gauge invariant.
Yes.
And then you look for representation of that non-gauge invariant object. To me, it just doesn't sort of hang together. So I suddenly realized that there was also the same question I was asking about what little partial d was and why d naught was unique and such. And then it occurred to me that maybe what you're doing and what is normally done anyway in 3+1 is that on the horizon, one is fixing once and for all the internal vectors, right, the internal space.
Mm-hmm.
And then the condition is really on the n-binds, that the n-bind should be such that some n sub I times the n-bind is the normal, because you know what I mean? I mean,
mm-hmm.
The normal has a vector index, and we can only talk about normal really in space-time. So is it possible that you're implicitly assuming somehow that there is an internal space fixed on the horizon, which really would correspond to allowing only global gauge transformations, which somehow seem to come at the end?
Yes. So I should
you think to me that unless you do that, the intermediate steps are not well defined.
Yes. So if you don't explicitly say that you would shrink these S's to a point in which limit they become gauge invariant again, then you should probably put this breaks local gauge invariance in the first box already there.
Well, my difficulty with your point, with that point, would be basically that looking for representations seems okay. All right. to me, that looking for representation seems awkward for this algebra, because the algebra, I mean, each object is really defined in a given gauge, and then one is talking about some, at the end, then one is also imposing gauge, the Gauss constraint and such thing, and so it just doesn't make sense to me. Okay, but the second thing is that in the last transparency, which you did not really mention, right, the one which has to do with the definition of non-rotating horizon, I guess,
Yes.
and non-rotating isolators. In the very last box, you have a condition, right, which what non-rotating really means. And the first two boxes are kind of standard ones.
Mm-hmm.
The third one is the one where you talk about non. And that is all done in terms of this vanishing of Newman-Penrose coefficient, etc.,
Mm-hmm.
which is all very, I mean, that is how it was done also in 3+1 in the very first paper. But that's very, very awkward and not, I mean, we don't understand the meaning of that really. And therefore it was replaced, right, in the subsequent papers by saying that you have got this rotation one form, little omega, and that one form should have zero curvature. That is what we mean by non-rotating.
Mm-hmm.
Is there something like that perhaps possible here, or
I
you
don't know.
haven't thought about it, or you have thought about it and did not work?
So what is true is that if you take the definition of the third box, then the calculations work. And the calculations are actually quite involved if you look in the paper. So after we got them working for this definition, we didn't try to get them working for some other definition.
Right, but that was also true in 3+1. I mean, first this very awkward definition in terms of Newman-Penrose coefficient was introduced. And then, one did a lot of long calculations to get the symplectic structure and such thing. But
I completely agree with you.
The whole thing
It should be possible to do that also with this different definition, but we just haven't done it yet.
Right. So I think it might be actually simplified. It might be simpler. It might be simple. That's what happened in 3+1. That was the definition in terms of curvature of this rotation one form omega, the pure gauge. That is what is used, and that sort of makes complete physical sense, and is mathematically elegant. And then when that was used in a covariant formulation of the symplectic structure, the symplectic calculation was in fact much easier than in terms of the Newman-Penrose coefficient. So you might want to think about that.
Okay.
Thank you.
Question?
Go ahead.
Yes, so one of the prime motivations for setting up the calculation of black hole entropy in higher dimensions would be to compare to the calculations in string theory for extremal black holes. For example, the Strominger and Vasa in 5 dimensions. But can you do that, or extremal black holes not included in the class of spacetimes that have isolated horizons?
Well, we haven't looked into that yet, actually. So I'm not even sure if this extremal condition can be implemented in some well-defined way. I mean,
does anybody know? I mean, my impression is it would be a very good. We've been saying for a long time that if we could extend our calculations to 5 dimensions and extremal black holes, we could compare with the results of Strominger and Vasa. And it would be very good to be able to do so.
So what is known, Lee, is that the definition of isolated horizons, of course, go through with or without extremality, and there is no problem with that. The problem is really that the original formulation of walled entropy does not work for the extremal case, because that formulation basically really makes a very critical use of the so-called bifurcate horizon. It is really based on perturbations around stationary black holes, or going from one stationary black hole to another stationary black hole, and one reduces all the calculation to this bifurcate horizon, and the bifurcate horizon doesn't exist in the extremal case. So the first part of your question, namely, are extremal horizons included in the isolated horizon framework? The answer is yes. But the additional complication may be that since this whole thing is sort of motivated by walled entropy kind of ideas, that formula or derivation doesn't go through in the extremal case.
That's very
But
interesting.
independent of
So
that, one might try to see what happens in 5 dimensions.
yeah, so that, on the one hand, that suggests that the techniques used by Strominger and Waffe don't generalize to general black holes, which history has shown they haven't been generalized. Maybe this would explain why.
I mean, there's a correlation, but I don't think it explains why in some sense. I mean, yeah, there's a correlation. Both those things are real true. Actually, then along the same lines, maybe I can ask Norbert a further question. In passing, he mentioned that, well, for general theories, the area operator is like the wall entropy. But I thought that this was really done for very special class of general theories, right? I mean, you don't have a proof that this is the case for completely general case, or
yes,
do you?
no, the proof is just for the theories which I stated there, which is Lance's Lovelock gravity and with non-minimally coupled scalar field. Now, we commented in the paper with Yasha on the case of generally covariant theories. However, there is some problem because, I mean, first of all, you have to handle the phase space and quantize the complete phase space. Now, there is a result that you can rewrite such a generalized theory as general relativity non-minimally coupled through very complicated tensor fields. But these tensor fields are then also like symmetric tensor fields of higher rank, and we don't know how to quantize them using loop quantum gravity. So no clear, no clear statements can be made there. But it might be conceivable that the same thing should go through for arbitrary theories.
Yeah, but we do know how to quantize these abelian tensor gauge theories and methods of loop quantum gravity. There are some papers about that a long time ago.
But yes, they are a form, so they are antisymmetric forms, and these are symmetric tensors, so they have like symmetric tensor indices.
Oh, okay. Yeah, you're right.
So just one last clarification. I'm still confused about your gamma naught a little bit. I think if I assume that in fact you have fixed the internal space on the boundary, on the horizon, then I understand what gamma naught would be. Then again, gamma naught would be indeed unique up to subject to those conditions you wrote down on transparency 15, namely the derivative of n prime and derivative of s prime and derivative of e equals 0. That gives you a gamma naught. But what I'm not clear about is that if in fact all those derivatives are 0, then isn't gamma naught flat?
No, the curvature of gamma naught is essentially the curvature of the horizon slice H.
This is because it is on a non-trivial bundle, or what? I mean, I'm still confused. If in fact does the connection defined with gamma naught kill all the verbines from your equations you wrote down, d of n prime, d of s prime, and d of e prime equal to 0? Is it saying it kills all the verbines or not? Maybe it's not saying that, and I didn't understand that.
Well, it's killing this double pullback of the field line and the n and the s, but that doesn't make it flat. So if you go through the explicit calculation, you find that the curvature R0, if you take the ij of the R0 and make it into tensor indices on H again with this double pullback of the field line, then this is exactly the Riemann curvature of the horizon slice H.
Good. So the statement is that because the indices are suppressed, so d of n prime equal to 0 just means on the internal index. Is that correct?
Yes.
Okay, good. And d of s prime equal to 0 is also internal index.
Yes.
Whereas d of double pullback of e prime means both space and internal index.
Yes. Or if you would write it here in this form language, then it would be antisymmetrized, and then this would drop out. Then.
Antisymmetrized. Okay. So just antisymmetrized. It's not the full D is not 0 either.
Yes.
Okay. Thank you. That clarifies. Thank you.
More questions? Okay, let's thank Norbert again.